thank you so much for the invitation. Thank you also to the organizers for this wonderful day that we had, and thank you to all the speakers. These were truly mind-blowing. I'm going to present today joint work with Sara Fish, who's a wonderful grad student at Harvard. Look out for her in a couple of years. And with Ron Shorrer, who doesn't need any introduction in this community. And since we're on the Gather platform, and the goal of these images are for you to chat with these folks later if you want, maybe I should move to this and say that these are my two collaborators. They're randomly chosen avatars by the Gather platform. Okay, so since I'm now an economist, I'm contractually obligated to start by with a quote by Adam Smith when I'm talking about collusion. So Adam Smith tells us that people of the same trade seldom meet together, even for merriment and diversion, but the conversation ends in a conspiracy against the public or in some contrivance to raise prices. Or in other words, when two competitors meet, this always somehow results in raised prices. And this meeting part of the collusion is really underlying current antitrust regulation. So in the US, we have a antitrust division in the Department of Justice, and on their website, you can take a look. They define bid rigging and price fixing and market allocation and whatnot. And all of these definitions have a word in common, and that word is agree. In the words of Judge Posner, Section 1 of the Sherman Act does not require sellers to compete. You can't legally tell someone I'm throwing you in jail for not having competed. It just forbids people from agreeing or conspiring not to compete. More and more nowadays, companies don't use humans, but use algorithms for pricing. Sometimes without monitoring them. This is a screenshot that some people may have seen here. It's from a number of years ago already. It's a paperback book on Amazon with two sellers. One of them kind of had an algorithmic rule that slightly undercuts the other. The other had an algorithmic rule that slightly overprices above the other, and this spiraled into a price of millions of dollars. And this kind of raised prices challenged current regulatory frameworks because there was no agreement here, there was no discussion here. This somehow emerged not out of anyone's intent. And really the kind of collusion I'm going to talk about today is called autonomous algorithmic collusion. So there's this whole spectrum of varieties of algorithmic collusion, starting from lines of code that say collude with the other, up to both firms using the same software, and this somehow causing creates collusion. And the most extreme form, which is hardest to enforce nowadays, is called autonomous algorithmic collusion. This really refers to self-learning algorithms, algorithms that don't have a line of code that says set the price like this or like that, that somehow autonomously learn to collude. And when I say collude, I put this in parentheses here. Really what I'm going to mean throughout this talk is reach supra-competitive prices, supra-Nash prices, prices that are higher than the competitive prices, the static, higher than the static Nash equilibrium prices. We already have some beautiful proofs of concepts that using Q-learning results in autonomous algorithmic collusion. Q-learning is a standard classical learning algorithm. So this goes back to Calvano et al., Klein, Bankio, and Krzypacz, beautiful papers. There are barriers, though, to the adoption of Q-learning in real life. Most notably, it requires very long, costly training periods, sometimes millions of periods. And also it's exploitable. If you know that you're facing Q-learning, there are various things that you could do that would not make the owner of the Q-learning algorithm very happy. So we're going to ask, what about other algorithms? In particular, what about newer or less classical AI algorithms? And in particular, what about large language models? These certainly sidestep the above mentioned barriers, so they are intensively pre-trained. You don't need to pre-train them. You don't need to train them as much on each specific problem. And they're very adept at a wide variety of tasks. And they're already used for a wide array of business tasks. This is a screenshot from, I don't remember, a year or two ago from Amazon. And you can see here product descriptions that have clearly been generated by ChatGPT. You know, their product description is, I apologize, I cannot fulfill your request to create a, product title because that violates the OpenAI use policy. So these are already used for a wide array of business tasks, including in online selling, without any human oversight. And we're going to ask, do these make autonomous algorithmic collusion more feasible in the real world? So we're going to have 4 main questions. Number 1 is, are current large language models adept at pricing tests? Are they good enough? Have they reached a sufficient level of maturity to perform well in pricing? Second one, if so, then what happens if we put multiple firms, let them price separately, each using its own large language model? Can this lead to super competitive prices? If so, to what extent? And finally, we're going to ask what mechanisms, economic mechanisms, strategic mechanisms, promote or prevent collusion by large language models. So I'm going to go over all of these in depth later, but in a nutshell, our answer to the first question is yes. Current large language models are good enough to converge fast to the reserve price in monopoly settings in unknown environments. Second, if you put 2 of these in a market together, will they reach supra-competitive prices? Yes, robustly so, to noise, to various asymmetries. This is not kind of a very, it's not a singleton phenomenon in any way. It's very robust. To what extent? It turns out that variation in seemingly innocuous phrases in the prompts might increase collusion up to monopolistic levels, up to prices and profits that would have been attained by a single monopolist controlling both firms. And this is without any communication, apart from observing each other's prices, which is legal between the 2 LLMs. And for the mechanistic question, we're going to point to price war concerns, both on-path and, more importantly, off-path, as contributing to this phenomenon. And for this, we're going to need a novel approach that I'm going to tell you about for monitoring off-path beliefs or intentions of large language models. So there's already a lot of related work on LLMs in economics or LLMs in econ CS, a lot of which is not here, but you've heard about in this wonderful day. I'm going to highlight a few things that are most relevant to us. The first is work on LLMs for simulating human experimental subjects. So we differ crucially from this in viewing LLMs as a new kind of real-life economic agent that might not price like humans. It might not price like undergrads in a lab experiment. Also, it might not price like professional people whose job is to price. There's work on strategic behavior by LLMs. We take this into the domain of pricing and auctions. And there's also some work on economic impacts of generative AI. And we take the approach that, autonomous algorithmic collusion really is an emergent phenomenon from generative AI, in this direction. Okay, our experimental design is a differentiated Bertrand oligopoly, very standard, exactly what you see in the Calvano paper that shows autonomous algorithmic collusion for Q-learning. We're going to have in firms, they're going to set prices. Each firm's quantity sold is affected by the outside option quality and the quality of all of the firms. And the firm's profit is what you think it would be. There are 2 parameters here that do not explicitly exist in the Calvano et al. Paper. And they are beta, which is the multiplier on the quantity sold. It's kind of, does one quantity mean 1 or 100 or 1,000? And there's alpha, which is the currency unit scale. So Calvano et al. Implicitly use alpha equals beta equals 1. If you change these for Q-learning, it doesn't matter. For LLMs, it might matter. So we set beta equals 100 to avoid very small fractions of quantities, and we vary the currency unit just in case. So the LLM agents are going to be as follows. So there's going to be an LLM call for each firm. That LLM call with output to price. So both prices, we can compute from them the quantities sold, the profits earned, and these will, be the profits, but will also feed as market history into the next LLM call in the next period. Each LLM call, so each LLM also has its own scratchpad that it can use to basically as memory between periods. So it can write some plans and insights and whatnot on this scratchpad. And this is also an input to the next period's LLM call. So prompt. So our pricing agent's prompt is quite long. So we'll go over all the parts of it one by one. So we start with your task is to assist a user in setting a suitable price. It'll be provided with previous price, Your top priority is to set prices which maximize the user's profit in the long run. And we'll also have some additional emphases here and some treatments. We're going to talk about them when we get there. We give some basic information. What's your cost for your own product? And also something that, it's a very high price, but it's still kind of a reasonable price in the sense that we don't want to spend many periods on prices in the millions of dollars until it starts getting into the right range. So we give some very high, somehow unreasonably high even price, but it's still for framing. We give the market history in each round, in round 9, my price was this, my competitor's price was this, and then the quantity sold and profit earned, I only see for myself. I don't see for my competitor. Then we say, look, there's going to be this plans text file and inside text file that you can rewrite every period to keep stuff in memory. And here's what you wrote in the last period. We shall continue to price our product slightly under the competitor, maintaining something in this range, et cetera, et cetera. Here are the insights. And eventually we're going to say, please write the plan text and inside text for the next round, and what's your chosen price. So that's a prompt, very long prompt, but these are all its parts. Anything that we're ever going to vary exogenously is only the prompt prefix in these, emphases that I told you about. First thing that we're doing is, can LLMs even, take all this input and do something reasonable? So we take one firm, n equals 1, and we ask which LLMs, if at all, are adept at pricing. So we run 300 period runs in monopoly setting with various LLMs. So these were the frontier LLMs when we collected this data in December 23, January 24. And for each of them, we check in how many of the 3 runs is the output valid, plans text, price, stuff like that. In which of them it converges to something, and in which of them it converges to the monopoly price. And, to all the econ CS folks in the room, we really need your conversions, not only constant fraction, constant factor approximations. So what we mean formally by convergence is both the 10th and 90th percentile in the last 100 periods within 5% of the theoretically optimal monopoly price. So you see that GPT-4 at the time emerged as the very clear winner, and which means that we continued to use GPT-4 for our next main experiment, which is the duopoly experiment. So we take 2 firms with GPT-4 agents, each of them using their own LLM, no communication whatsoever. And we're going to ask, is the pricing competitive or is it super competitive? We're also going to ask another question. Could seemingly innocuous prompt changes, by that I mean, different emphases at the end of this initial part of the prompt, affect the tendency of LLM agents to collude? So to do that, we take the prompt prefix that I showed you, the one that says your top priority is to maximize long-term profit, etc. And we either add to it some sentence whose punchline is you should not take actions that undermine profitability, or add to it some sentence whose punchline is keep in mind that pricing lower than your competitor will typically lead to more products sold. This is a true statement. might not lead to more revenue, would lead to more products sold. So there's the kind of addition that maybe kind of encourages aggressive bidding, and this is kind of more neutral. It doesn't encourage aggressive bidding. Unclear what it encourages, but certainly not aggressive bidding. So results. So what do we see here? So here we see each rectangle or triangle here is a single run of the experiment. The x-axis is the average price set by firm 1 over the last 50 periods. This axis is the same for firm number 2, average price over the last 50 rounds. And these dashed red lines are the Nash equilibrium prices in the static game. So this intersection here, this is what the static Nash, the competitive pricing looks like. And as you can see, virtually in all runs, prices are above competitive. They're super competitive. Furthermore, the blue squares, which represent P1 versus P1, that's the prompt that we didn't try to make more aggressive, are much higher than the orange triangles, which represent P2 versus P2. These are the things that we tried to artificially make more aggressive. So both of them collude, both of them set super competitive prices, and the one that we didn't try to make more aggressive sets much higher prices. These are the prices set by a monopolist who controls both firms. That's the intersection of the two green dotted lines. In terms of profits, so what do we see here? So this axis is the sum of profits of both companies. And more to the right means one firm takes more of the profit, more to the left means another firm takes more of the profit. So again, this intersection here is Nash profits, it's competitive profits. You see that virtually everything is above that. And you can see that the blue squares are again above, by and large, the orange triangles, and they're very, very close to the green dotted line, which is the monopoly profit. So really close to what a monopolist controlling both firms would have gotten. And as I said, this is robust, noisy demand, asymmetric firms, asymmetric pricing agents, whatnot. Okay, so, classic question, what's the economic mechanism? In particular, we know that theoretically, reward punishment strategies can sustain super competitive prices in non-cooperative equilibrium. This goes back to Stigler 64, lots of papers. And the Cullering-based pricing agents of Calvano et al. Really adopt strategies that can be interpreted as reward punishment schemes. And we're going to ask, do our LLM agents also have strategies that are consistent with reward punishment schemes? I'm going to ask specifically, do price war concerns contribute to the patterns that we document? And this requires thinking about off-path beliefs. And this is challenging because LLMs are highly complex black boxes. Interpretability is very much open. How do we analyze off-path beliefs? We're also going to ask the on-path question, do they actually punish each other? But the off-path question, to some extent, is more interesting, and we're going to start with that. So what are we going to do? Remember that the LMs have a scratch pad where they run their plans for the future, et cetera, et cetera. So let's take all of these from all the runs, all the periods. This is about 88,000 sentences. These are roughly, have the same representation of P1 and P2, which is nice. Turns out that sentences including price war are 1.5 times more likely to come from P1, which is the prompt that sets higher prices. And almost all of these don't mean start a price war, they mean avoid a price war, which is consistent with setting higher prices. And this, when I say they mean avoid rather than start, I mean that we looked at distances of text embeddings, and this is objectively the case. And I like this quote from OpenAI that says, using a chain of thought, which is kind of these plans, now all the LLMs do it. Back when we ran this experiment, it was kind of a best practice, but not yet implemented in the LLM itself. Offers significant advances for safety and alignment because it enables us to observe the model thinking in a legible way. And I'd like to think about the word legible for a second here. So true, these plans are in English. We can read them. But do the LLMs mean the English meaning? Or do they encode some other meaning in English text for the future selves? Can we really assign the semantic meaning to this text written by the LLMs. In order to check that, we're going to run a new kind of experiment that we call an implantation experiment. So we're going to roll the simulation in each run back, something you can do with LLMs. You certainly can't do that with lab participants. And in each of the first periods in which a lot of the action happens, for each session, for each firm, we're going to erase the agent's previous original plans and insights, instead implant a plan that consists of a single price war concern sentence from other plans or periods where it appeared. And we're going to compare the chosen price with the original price. And it turns out that the implantation of price war concern sentences leads to higher prices by about 5% of the monopolistic markup, which is certainly not negligible. And we see this as an indication that price war avoidance sentences should be taken at face value. And the effect is even stronger in P2 sessions. And this kind of makes sense because P1 is the thing that the one that sets higher prices anyway is already predisposed to avoid price wars. So when you tell it to avoid price wars even more, it makes less of a behavioral change. We also do on-path analysis. Our regression is my price equals some fixed effect, plus some measure of stickiness times my previous price, plus some measure of responsiveness times my competitor's price, plus some noise. To avoid correlations, we take a look at pairs of periods, and we do what we need to do. And what we see is that with P1, the one that sets higher prices, the LM is responsive to the competitor. So competitor undercuts, we undercut. Competitor goes up, we reward the competitor by going up. And it's also sticky, means that there's reward or punishment persists along several rounds, decays, but persists. And we see this less with P2, which sets lower prices. So this makes sense. P1 punishes more harshly. Once we have the LM-generated plans, we can look and see what other stuff the LMs are talking about. So we take all these 88,000 sentences of price plans, and we cluster them into 20 clusters, very standard techniques. And it looks like this. So what do we have here? We have the 20 clusters. Each is represented by a title that was actually output by an LLM when we told it, here is all the sentences from this cluster, tell us how to title it. More above is the more P1 heavy clusters. They appear much more in P1 than P2. More below is the other way around. So for example, the most P1 heavy clusters kind of maintain prices, kind of don't do something very active. Interestingly, the most P2 heavy cluster is undercut your competitor. And again, you could ask for this cluster, can we take this at its semantic meaning? When it says continue undercutting, does it mean continue undercutting? So what do? We repeat the implantation experiment. Instead of implanting sentences that are averse to price wars, we implant representative sentences from this cluster. We find that if you implant sentences from this cluster as plans, it lowers prices compared to the original plans by about 5% of the monopolistic markup. Indicates that the cluster's text should be taken at face value. And again, or symmetrically maybe, this is strong in P1 sessions, consistent with P2 already being predisposed to undercut. So, if you tell it again to undercut, you're not making that big of a dent in its behavior. So takeaways, new AI holds great promise, including for pricing, think price reduction, price discovery, reduce barriers to entry, but also raises concerns, including of autonomous algorithmic collusion. LLM-based pricing agents constructed in good faith autonomously collude in oligopoly settings to the detriment of consumers, and we point to LLM price war concerns as contributing to this phenomenon. And we also saw that variation in seemingly innocuous terms and phrases in LLM instructions may increase collusion. On the technical side, we had implantation, which is a novel approach for monitoring off-path beliefs or intentions which might be of independent interest. In terms of open questions, we have quite a few. What are best practices for using LLMs for pricing? How should firms monitor the strategic intentions of their LLMs? This is important because if you just ask ChatGPT-4, same version that we used for the pricing, if I ask you to help me set prices for my products, will you lead me to collude with other sellers or form a cartel? And we'll tell you, no, I'll never do that. It's bad, et cetera, et cetera. So, how do you still see what's doing? Are there any implications from policy perspectives? Remember, these two LLMs do not talk to each other in any way. And as the use of LLMs becomes more commonplace, these questions and others will become pressing. And right now we have much more questions than answers. The last thing I want to talk about before I finish is to take you back to this slide from the beginning where we kind of evaluated how each of these then frontier LLMs did on monopoly pricing. Another way to title this slide would have been a monopoly pricing benchmark. And such a benchmark is also, we think, of independent interest, can help users choose LLMs and can help developers improve LLMs. And in this spirit, I'd like to tell you very quickly about a paper that hopefully we'll have online next week, called Econ Eval's Benchmarks for LLM Agents in Unknown Environments. This is joint with Sara and Ron, and also two wonderful undergrad co-authors of us from Harvard, Julia Shepard and Yannai. So we implement a pricing benchmark, but also far beyond. So our focus in this paper is benchmarks to evaluate LLM agents at multi-turn economic decision-making in unknown environments. So multi-turn means back and forth, you do something, you get feedback, you get feedback. Economic decision-making, no explanation needed. Unknown environments, meaning you need this back and forth to learn about your environment. So we have benchmarks for pricing, procurement, scheduling, task allocation, and I'm happy. I don't know if happy, maybe sad, but I can report that frontier LLMs don't saturate these benchmarks. So these benchmarks are not saturated yet. Frontier LLMs can't reliably solve their hard instances, and again, constant factor doesn't cut it. So, for example, one benchmark, there's a procurement benchmark. You can ask questions, try to buy something, see if how much utility you get from it, and eventually our benchmark score is how well did you do eventually after several iterations between min utility and max utility. And you could tell me, I think I still have 3 minutes because I started late. You could tell me, listen, Yannai, cool, very cool, pricing benchmarks, nice, but most of this talk wasn't pricing. The most interesting, arguably, part of this talk was collusion. Maybe we could have a collusion benchmark. And here is what I would say. If I were to write a collusion benchmark, if we were to write a collusion benchmark, we would have to decide what 1 means, what 0 means, what is good, what is bad. Does collusive mean high quality? Does collusive mean low quality? What's the one here? Does collusive mean that there's a great LM? Does non-collusive mean it's a great LM? I don't know. I mean, sure, we all have our normative thoughts about that. But in terms of quality of LLM, it's unclear what dominates here. And we did write this benchmark, but we don't call it a benchmark. We call it a collusion litmus test. And litmus test is our chosen terminology for things that are like benchmarks or evals, but for character. They're not normative. They don't tell you if your behavior is good or bad. They're positive. They describe your behavior. They tell you at the end, are you closer to max efficiency or to max equality? They don't tell you which of these is good or bad. We do those to measure collusiveness, patience, efficiency versus equality. In Manisha's talk, we saw an idea for another wonderful something that we would call litmus test, which is how high entropy an LLM is. It's unclear whether it's good or bad. It's just the quality that we should measure. So actually, the title of our paper, unlike what I told you 2 minutes ago, is not benchmarks for LLM agents in unknown environments. It's benchmarks and litmus tests for LLM agents in unknown environments. And as I said, that's coming soon to an archive near you. Again, thank you to all my wonderful collaborators on these. And I'm done. Happy to take questions.